Hi all, I welcome you all to the next lecture today. The agenda is to see some problems on gas mixtures and on ideal gas concept. In previous lecture, the concept of ideal gas and gas mixture was covered, and we have seen some of the numerical problems based on ideal gas concept and gas mixture. Today we will try to solve around 5 problems based on ideal gas concept and gas mixture. Here Professor Ravi Kumar, School of Mechanical Engineering, Shastra DMTV University, Tanjore. So let's gear up for the numerical problems. I would request to each and everyone should have a calculator with you so that fastly you can verify the answers. So let me start the problem statement. So if we look at the first problem for today, sixth problem in the series, what is the minimum amount of work required to separate 1 mole of air at 27 degrees C and 1 atmospheric pressure, assume composed of 1 by 5th of O2 and 4 by 5th of N2 into oxygen and nitrogen each at 27 degrees C and 1 atmospheric pressure. So it is asking you to basically to find out the work required to separate 1 mole of air into these two constituents and their corresponding you know compositions have been given. Look at the process actually occurring at a constant temperature. So more or less it is a isothermal process, and for the isothermal process we know a standard formula to calculate the work required. It's nothing but P1 V1 ln of P1 by P2 or P1 V1 ln of P2 by V1. So as you are here you see basically volume is not mentioned, so we will be basically dealing with only pressure variations, right? So by using the pressure variations we can find out the minimum work required. So what all properties are needed? We need characteristic gas constants, right? That is expected to be calculated, and gamma value for O2 and N2 need to be calculated. If you know, then directly you can proceed with. All right, and direct it is a straightforward formula based problem, right? So you can directly find out the minimum work required for each constituents to be separated, right? Separate for O2 and separate for N2. If you add it, total minimum work required can be calculated. So first of all, we will find out what is the total content of O2 and N2. So it is clearly given, it is 1 by 5th of O2 and 4 by 5th of N2 in the total mole. So we can say the mass of O2 is 1 by 5th of 1 mole, right? So that is coming around 0.0064 kilogram. And mass of N2 is 4 by 5th of 1 mole. It is coming around 0.0224, right, kilogram. So directly you can calculate these two values. Hmm. Now proceed. So mixture pressure at 1 atmospheric, temperature is 300 Kelvin, which is clearly mentioned here. So partial pressure of O2 is 1 by 5th, right, atmosphere, and partial pressure of N2 will be 4 by 5th of 1 atmosphere. That's the one thing. Now, so minimum work required is separately work required for the oxygen and for nitrogen. So we can say mass of oxygen, characteristic gas constant of oxygen, temperature 1 of oxygen, ln of final pressure of oxygen by initial pressure, right? Similarly here if you look at same formula can be written for nitrogen as well. Now look at this is nothing but partial pressure basically. So final pressure will be 5 and starting from 1, right? That's why 1 by 5th, and here also nitrogen is starting from 4 and going to 5, so 5 by 4 with the final pressure by initial pressure. So you substitute the value, mass already you calculated, right? These are the mass, right, which you directly got. And these are the values of pressure ratios, right? Final pressure and initial pressure ratio. So you can substitute these values here to get the minimum work required in isothermal. So this isothermal, as earlier said, is a constant temperature. So isothermal process, you can substitute the value of mass. This you have already calculated 1/5 of a single mole, right? Single mole. So directly you can calculate. Clear? So this is over. Like that you can directly solve. Let's go for the next problem. 0.1 meter cube of hydrogen initially at 1.2 megapascal, 200 degrees C, undergoes a reversible isothermal expansion to 0.1 megapascal. Find the work done during the process. Again, it is isothermal process. Heat transfer and entropy change of the gas. So volume is given 0.1 meter cube. Hydrogen is the gas. Initial pressure and temperature are given. It is undergoing through the isothermal process to final pressure. So you know P1 and P2. So you can use directly formula work done during the process is equal to P1 V1 ln of P1 by P2, and P1 is 1.2 megapascal, P2 is 0.1 megapascal. Volume 1 is already given, pressure 1 is also given. Directly you can calculate first part of it. If you go to the second part, heat transferred, right? So heat transfer is nothing but work done basically. So whatever you calculated, that itself is the heat transfer. Entropy change for isothermal process, you can calculate right using the PV is equal to is equal to constant equation. From there you derive the equation for entropy change, that is nothing but equal to whatever you are taking a formula for the work transfer. So process is something like this. Isothermal process on PV diagram you can represent in this way, right? If you want to represent over the temperature entropy diagram, it will be a horizontal line, right? This is the process. So characteristic gas constant, first you find out, that is universal gas constant divided by the molecular weight of hydrogen, that is 2, that you calculated here. So mass can be calculated by using the ideal gas equation of states P1 B1 divided by RT1. So this is the mass that you calculated. So it is a reversible isothermal expansion. So final temperature, initial temperature both are the same. Final pressure is also given. So enthalpy change is mcp T2 minus T1, that is 0. Right. So heat transfer is equal to the directly work done. Right. So work done basically is P1 B1, that can be written as RT. Right. RT ln of B2 by B1, B2 by B1, or RT ln of P1 by P2, pressure 1 divided by pressure 2, and pressure 1 is given 1.2 megapascal, which is written here, and pressure 2 is given 0.1 megapascal, which is here. And in place of P1 B1 I have written RT1, right? RT1 R already we calculated, which is here, and T1 is here, so you can substitute the value here. So you can go you can get the value directly for heat transfer basically is equal to the work transfer, that is 4886 kilojoule. So work done is equal to the same thing. Change in entropy is equal to mcp ln of B2 by B1 plus mcp ln of P2 by P1. This formula can be applicable to general thermodynamic process. So B2 by B1 is nothing but basically P2 by P1, right? And this thing you can directly already those things are given, so you can use those and can substitute the value here. All right. So like that one can easily solve this problem. Entropy change can be calculated by using this formula, and the Cp and Cv particularly you need to calculate by using the formula called Cp is equal to gamma R upon gamma minus 1. R already you know, gamma for H2 is diatomic, right? You can find out that is 1.4. So using formula directly you can get Cp and Cv, you can substitute the value here. So ln B2 by B1 that is nothing but already we calculated P1 by P2, which is written here, and plus MCB P2 by P1, that is again same formulation. P2 is 1 megapascal, this is 1.2 megapascal, same thing it is. At two times you are writing this because B2 by B1 is also equal to the P1 by P2, which I already written here, and P2 by P1 P2 is basically 1 megapascal, right? 0.1 megapascal is 1.2 megapascal. Both terms are same, right? Here and here. Things are different. Here P1 by P2, here it is P2 by P1. And Cp and Cv directly you can calculate in this way. Cp is equal to gamma R upon gamma minus 1, which is 14.55, and Cv is equal to R upon gamma minus 1, which is 10.4. Clear? So this is the first problem, right? That's what we asked, right? Entropy change we calculated, heat transfer is equal to work transfer, that you have already calculated. Take the next problem. Just go through the statement. Statement is saying an ideal gas of molecular weight 30 and gamma is equal to 1.3 occupies a volume of 1.5 meter cube at 100 kilopascal and 77 degrees Celsius. Full stop. The gas is compressed according to the law PV to the power 1.25 sorry is equal to constant to a pressure of 3 megapascal. Calculate the volume and temperature at the end of compression and heating, work done, heat transfer, and the total entropy change. So first you need to understand which sort of this problem is. This problem is basically polytropic process, right, which is clearly given in that, and you need to find out the volume, temperature at the end of compression, then yes, and heating, work done, heat transfer, all sort of things you need to calculate. So how to proceed for this problem? You can proceed in a similar way. First, you find out the characteristic gas constant by using the what we say universal gas constant divided by the molecular weight. So this is coming like this, and gamma for basically look at this molecular weight is given, right, and occupies 1.5. Gamma is already given. So gamma is 1.3. Polytropic index is 1.25. So Cp and Cb can be calculated. Cb is equal to R upon gamma minus 1. Cp is equal to gamma R upon gamma minus 1. You can calculate. And these all parameters already given: 100 kilopascal, B1 is equal to 1.5, T1 is equal to 350 Kelvin, P2 is equal to 3 megapascal, which is 3000 kilopascal, right? These are the given data. And now work done, use the standard formula, right? P2 V2 minus P1 V1 divided by 1 minus n, or you can say P1 V1 minus P2 V2 divided by n minus 1. You know P2, you know V2, right, which is already given, and P1 V1 already you know, and n value already is given. So P1 is 100 kilopascal, B1 is 1.5, and P2 is given, and B2 you can calculate, right? If it is not given, you can use the formula P1 B1 to the power n equal to P2 V2 to the power n, right? So B2 can be calculated as P1 by P2 to the power 1 divided by n into B1. So B2 can be calculated. Use that V2, which V2 is coming around 0.09872 divided by n minus 1. So this work required is minus, because we are compressing. So for compression work will be negative. You are doing work on the system. So that is minus 584 point something. It is coming, right? That's the work required for compression. Next one is heat transfer. Heat transfer is equal to U2 minus U1 plus W122, and W122 already you calculated, and U2 minus E1 is equal to MCV T2 minus T1, and T2 is already given, and T1 is also given. So you can substitute the value and you can calculate, right? You can calculate. So look at the parameters. So here this is the initial volume, initial pressure, initial temperature, final pressure is given. Now question will rise, where is the T2? So T2 can also be calculated by using the isentropic relation. T2 by T1 is equal to P2 by P1 to the power gamma upon gamma minus 1 upon gamma, right? So P2 and P1 are given and T1 is given, so T2 can be calculated. So this you need to do from your end. So find the T2, then substitute the value of T2 here. So T2 is equal to T1 and P2 divided by P1 to the power gamma minus 1 for gamma. Gamma value is given 1.3. Just substitute and get the T2, then substitute the T2 here, which is 691 minus T1, and this is your work done already you calculated here, right? And for calculating work done, don't mistakes, right? Calculate V2 separately using the P1 B1 to the power n is equal to P2 V to power n. So B2 can be calculated, right, with the help of P1 B1. Then you substitute here and calculate this value. Change in entropy, use the general formula mcb ln of p2 by p1 plus mcp ln of p2 by b1. b2 b1 you know, p2 p1 you know, and mcp cp and cb value are known to you. Substitute the value. This is known as entropy change during this polytropic process. Like that you can solve, right? Take the next problem. Methane has a specific heat at constant pressure given by Cp. Now look at the equation of Cp, which is a variable with temperature. Kilojoule per kilogram mole K. When 1 kilogram of methane is heated at constant volume from 27 to 500 degrees C. So it is getting heated, right? Keep in mind. If the initial pressure is 1 atmosphere, calculate the final pressure, heat transfer, work done, and change in entropy. Right? That's been asked. So how to do? Cp is given, right? So what are given parameters? P1 is given, T1 is given, mass is given 1 kilogram. So characteristic gas constant can be calculated for methane, right? So methane's formula you know, CH4, carbon 12, right, and hydrogen 1. Methane is CH4, carbon 12 plus hydrogen 1 into 4. So total is 16 is the atomic mass, right? So characteristic gas constant is equal to universal gas constant divided by 16, which is coming around 0.51964 kilojoule per kilogram Kelvin. And final pressure is 261 kilopascal, right? Final pressure is 261 kilopascal. So what you need to do? Initial volume, calculate. So volume is not changing because it's inside a container, so that is a constant volume already mentioned here. Methane is heated at constant volume from 27 to 500 degrees C. Initial pressure is given. Now it is a constant volume, so we can write the equation like P1 by T1 is equal to P2 by T2, right? P2 by T2, and T1 T2 are given and P1 is also given. So can you calculate P2? Yes, you can calculate. So just write equation P1 by T1 is equal to P2 by T2, and P1 is already given 1 atmosphere, T1 T2 are here, right? So P2 can be calculated, that P2 is here 261 kilopascal. You can calculate by using the expression P1 by T1 is equal to P2 by T2. Then you come to the volume 1, that is using the ideal gas equation mR T1 by P1, and volume is constant, so B1 is equal to B2, right? Now heat transfer is asking, so MCP dt, right? MCB dt, why CB? Because it's a constant volume process, otherwise it should be CP. So MCB dt, put the value of CB, which is here, right? Which is here, right? Now problem is this is Cp. So Cp minus Cv is equal to R. So Cv is equal to Cp minus R. So R value already you calculated, right? R value you calculated, that same value you can subtract from this and put the equation here. So M integration Cp minus R dt. So Cp is this, right? Cp, this equation is here, right? Which is given here. So just take this and put it here. Now question will arise, why I am dividing by 16. I am dividing by 16 because this unit was kilojoule per kilogram mole K. So if I divide this by atomic mass unit, my unit will become kilojoule per kilogram Kelvin. So I have divided by the unit mass, which is 16. So this was on molar basis. Instead of molar basis, I written a simple form by dividing the atomic mass unit. So it is becoming kilojoule per kilogram Kelvin. So I can substitute now here Cp minus R. So Cp equation is this, and minus R. So only one variable is T. If you integrate this between 27 and 500 degrees C, you can get this value. Just integrate this between 27. Convert these into Kelvin, right? First, right? Convert these two values in Kelvin and put here limit, lower limit 27, highest is 500 degrees C, and just integrate this, you will get this value. Work done. will be 0 in this case because PdV is 0, volume is not changing. So now change in entropy. So use the TDS relation for closed system. TDS equal to du, right? PdV is not there. Du, that is mCV dt. Cv is Cp minus R dt. So you just substitute the value of Cp minus R here into dt, and ds just integrate between 300 and 773. This complete equation, right? This complete equation you are going to solve. If you solve this, you can get the change in entropy, which is coming around 2.3822 kilojoule per kilogram Kelvin. Try from your side, solve this carefully, right? Cp value already is here. This same thing, this equation you will be writing there, and you subtract the R value and put here, right? Divided by T dt, then integrate it. Take the next problem. A certain quantity of air initially at a pressure of 8 bar 280 degrees C has a volume 0.035 meter cube. It undergoes the following processes in the following sequence in a cycle. First is expands at constant pressure to 0.1 meter cube. Then follows polytropic process with polytropic index 1.4. Then a constant temperature process which completes the cycle. So understand, first is constant pressure process followed by polytropic process, then finally isothermal. Evaluate heat received in the cycle and heat rejected in the cycle, efficiency of the cycle, right? This is the problem. So what is given? Pressure 1, 8 bar, volume 1, this one is given, temperature 1 is already given, so I have written. Final pressure, right, expands to constant pressure, right? Final pressure is also same, right? So final pressure is also 8 bar, right? And final volume is given 0.1 meter cube. Polytropic index is given 1.4. Now draw the cycle. First is constant pressure expansion, polytropic expansion, then isothermal compression, which is completing the cycle. This is on PV pressure versus volume. Constant pressure expansion followed by polytropic expansion followed by the isothermal compression. So if you draw over temperature versus entropy, this is a constant pressure followed by the polytropic, then isothermal compression, which complete this cycle. So this is the diagram, right, showing the complete process or this is a complete cycle. So it has been asked, right, what is the total heat added and what is the total heat rejected in the cycle, and cycle efficiency need to be calculated. So process by process you need to solve this. So to find the mass, right, P1 B1 is equal to MR T1. So you can write it, get the mass out of it. P1 B1 by RT1, that is a mass. Similarly, what is unknown parameter at 2? At 2, I don't know the temperature, so I will use P2 V2 is equal to MR2, right? So mass is given, R is constant, P2 I know, V2 I know, and so T2 can be calculated. So T2 is equal to P2 V2 divided by mass into characteristic gas constant. So I got 1580. All right. Now go to the polytropic process. Next one is polytropic process. So in polytropic process, what you need to do? Unknown parameters need to be calculated. So P2 V2 I know, P3 already given, right, but V3 is not given, so I need to calculate, right, this one, and temperature also need to be calculated. So T2 by T3 is equal to P2 by P3 to power 1.4 minus 1 divided by 1.4, this is gamma minus 1 upon gamma. So look at the cycle, P3 will be here and P2 will be here. I already know here pressure and here pressure, same pressures can be used. All right. So another thing, T1 is equal to T3, which is already known, right? T1 and T3 already known, right? But problem is I may not be knowing the P3, so P3 need to be calculated. I know P1, P2, but P3 is unknown to me, and T3 is equal to T1. That is already is a process, right? T1 and T3 is there, and T2 already I calculated. So with the help of T2, T3, and P2, I can get the P3. So look at here this equation. So T2, T3 are known, T2 by T1 I can write this, and P2 is known to me and P3 is unknown, so that can be calculated. So P3 can be calculated 0.2 par. The moment I know the P and T at 3, I can get the volume at 3 by using the ideal gas equation of state, right? So B3 is also you calculated. Now heat received. So how to calculate the heat received? So apply the first law, Q is equal to delta U plus W. And what is W? That is PdV work, right? During first process, right? Take first process, constant pressure process. So this is P V2 minus V1. V2 is known to me. V1 is also known to me. Just substitute here. I can get the work done during the expansion at constant pressure, right? So process by process you have to go, which is coming around 52 kilojoule. So heat is mcv t2 minus t1 plus work, right? Cv value already given, right? Mass I calculated, I can substitute here, right? T2 and T1 is known to me, so I can get the heat, right? Transfer during process 1 to 2, which is coming as positive, that means heat is getting added. Now apply the first law to the process 2 to 3, that is polytropic, right? So polytropic process, work done is P2 V2 minus P3 V3 divided by n minus 1. I know all these parameters, so I can substitute the value, I can get the work done, which is coming positive. So Q is equal to MCV T3 minus T2 plus work done. So if I substitute the value of T3 and T2, T3 is nothing but T1 basically. So if I substitute this value, I am getting this as positive. That means this is also heat addition. So two heat additions I got, right? One in process constant pressure, another in the process polytropic, right? These are the two heat additions. Now go to the last one. So heat rejected in the cycle. Uh, Apply the first law to the process 3 to 1, Q delta U plus W. Now process 3 to 1 is isothermal, so there is no point of delta U. Only work done I need to calculate, that itself is the heat rejected. So work done is P3 V3 ln of B1 by B3, right? So just substitute here, right? So B2 for process 3 to 1 is B1 basically, right? B1 by B3, and B3 is known, P3 is known, B1 B3 I know, I can substitute the values. You substitute, you are getting negative, so negative means heat is getting rejected. This is the heat rejection, so which is coming around this. Now look at heat supplied is totally you have to add in process 1 to 2 and 2 to 3. If you add these two values, that is the heat supplied in the cycle, and heat rejected is this. So cycle efficiency can be calculated 1 minus heat rejected by heat supplied, right? Simple thing. So heat received minus heat rejected divided by heat received. Heat received means those two things you have to add. You have to add this one, right? This is here total heat, right? This and plus this you add, it is coming around 181. This is the heat received in the cycle, and heat rejected is this much. Just substitute here, you can get the thermal efficiency. You can get the thermal efficiency of the cycle. So like that you can solve. And work done is PdV, right? PdV. She's asking about apart from that, what he is asking is asking efficiency of cycle. With that it is over, right? So your problem is over with the heat cycle efficiency, that's all. So for today this much is enough. I am closing the discussion here, right? So if you are having any doubt in this, right, feel free to post in the comment section, right? And please go through some more numerical problems, right, based on this concept from your standard textbook, engineering thermodynamics by PK Nag, right? And feel free to contact me in the case if you are not able to get solution for any of the problems, right? Already I shared my WhatsApp number with you, right? See you all in the next class with a new topic, introduction to the real gas concept. So ideal gas concept and gas mixture is over, right? Please prepare your own notes going through the PPT, all right? And yes, make your habit to solve number of problems, go through the book, right? If you find any problem which is you think that is really challenging, you cannot solve that, please mention to me via WhatsApp, or you can write in the comment section. I will help you in solving those problems, right? So with this, basically your third unit is almost over, right? Third unit is almost over. In the next class with the real gas, we will conclude the third unit of engineering thermodynamics, right? So thanks for listening my lecture for today. Have a nice day. Good day.